Hello everyone, welcome to the class once again. I hope you're all doing good and you're in the best of your health. So till now we have already studied about the satellites and planetary motion and have studied about what is the time period, what is the velocity of a satellite. In the last class I was telling you that a satellite is moving in an elliptical orbit. Based upon this elliptical orbit, Newton and Kepler actually already gave that the planets are revolving in elliptical orbits. Kepler gave us some gravitational laws which are actually controlling this motion of all the planets, and we'll be studying today Kepler's law. Kepler's law, let me begin the class with understanding the planetary motion and what Kepler said about planetary motion, Kepler's law. Now Kepler said that he gave us three laws which actually control the motion of the planets around the sun. Now the first law is, it is a law of orbit that every planet is revolving in an elliptical orbit with sun at the focus. You see here in the last class I was telling you, if this is the sun and if sun is present at the focus of one of the elliptical orbits, the planets will be revolving all around here. This is the orbit of the planet, this is an elliptical orbit. This is what we have studied in the previous class. So Kepler said that every planet is moving in an elliptical orbit and these orbits are bounded orbits. Every planet revolves in an elliptical orbit. So you can take down this statement that I am saying. Every planet moves around the sun in an elliptical orbit and these orbits are bounded orbits. So elliptical orbit, one point, and these orbits are bounded orbits. This is the first one, second one. When I say bounded orbits, what do I mean by these bounded orbits? This means that these orbits are stable orbits. The net energy of the planets moving in this orbit will be negative. It will be lower than zero. In that case, when a body is having negative potential energy, that means negative total energy, that means the body is stable and it will be continuously revolving in this elliptical orbit. If the energy was positive, then the planet would be in such a state that it could leave the orbit and it could fly off. But we generally don't find this situation. The planets remain in this elliptical orbits and they move here. Now, sun is at the focus. Sun is at the focus and I'm drawing two focus here. One focus here also I'm drawing. So two focus we have. These are the foci of an ellipse. Now you see here planet is revolving. One time it will be at the nearest point with respect to sun. This is the planet which is revolving. And one time it will be further away from the sun. Planet at the second position. You see your sun is here. This point will be nearest to sun and this point will be further away from the sun. What is this position called? In the case of satellite, we have given you apogee and perigee as the farthest and nearest position respectively. Here in this case we have the nearest point is known as perihelion. The nearest point is known as perihelion and the farthest point is known as aphelion. Aphelion is the name of the farthest point. Now how can you remember this? It's very easy, as I told you in the last class. Do remember FANP, fan and P. This is the shortcut to remember. F farthest, aphelion, N nearest, that is perihelion. Do remember this. Farthest, aphelion, nearest, perihelion. That is what I have given you. Nearest, perihelion, and farthest is aphelion. That is what I have written here. That is easily you can understand with the shortcut way to remember fan P. Next thing, first law, they are moving in an elliptical orbit. And already I have told you, because the velocity is not as equated by L root gm by a, it is not the speed. And now one more thing, if the speed you take at 2 points, let me mark here speed as v1 and here the speed as v2, the planet speed, when it is nearer, it will be revolving with a higher speed compared to the speed when it will be further away from the sun. When it is further away from the sun, then its speed will be lower. So I am writing here v1 will be greater than v2. And we have seen this relation. When we conserve the angular momentum, in that case, we realize that the speed is more when it is nearer to the sun, and when it goes further away from the sun, the speed will be lesser. That is what I have written. V1 will be greater than V2. Next part, the second law of Kepler. The second law states that it's the law of area. Second law, law of area. Very simple law it is, law of area. Now this law says that the line joining to the planet and the sun sweeps equal area in equal interval of time. I am writing here the law, the line joining sun and the planet, the line joining sun and planet sweeps equal area in equal interval of time. Sun and planet sweeps equal area in equal interval of time. Hope that that's easily you can get that in equal interval of time. This is what is the second law says, that sweeps equal area in equal interval of time. And it's quite easy to understand with this statement what I mean to say with the second law. Suppose if I draw here again the position of the planet keeping the sun at one of the focus. This is the sun, and see, I'm going to draw the elliptical orbit in this way. This is the elliptical orbit. This is what we can observe. Now you see, when planet is revolving, let's say planet is here. At some time it is at this position. If I join this line with sun, if I join the line connecting the sun and the planet in this way, after some small time delta t, this planet will reach at this particular location, let's say making an angle d theta, let's say. In time dt, it moved from here to here and sweeping an area given by the shaded portion. This is what has been given in time dt. It has moved from this position to this position, sweeping an area. Now in the same time dt, if I take planet's another location, suppose the planet was here. Let's say the planet is here, and the same time dt it reached here. So if I connect these two positions, see what I'm going to obtain. I'm going to obtain the same time dt, this time it has covered this much distance, and the area that it has swept, that will be given as this. This will be the area that I am showing you with the shaded region. This will be the area. In the same time dt, the first case, planet has moved from this position to this position. The second case, it has moved from this position to this position. Kepler's second law says that in same time interval, the line joining sun and the planet sweeps equal area in equal interval of time. That is, rate of sweeping of area is constant. Now that means if I mark this area as delta A, this area will be also given as delta A. This you should be very well aware of. Both the areas will be equal, or let me write the law, dA by dt is constant. The same thing can be proved also. We can treat this as a triangle. We can show that the same thing can be proved also, but that proof is not required in our syllabus, that is not in our curriculum. So let's not get into the detail of the proof of this law of area, and let's directly switch to the third law. And before that, let me tell you about this law of area once again. Remember, you have to check this line. In some time dt it has moved here, this line has moved here. The area that it has swept, this will be the area. This has to remain constant. If you take a large time interval, let's say the time of, let's say 1 month. In 1 month, the planet has moved from here to here. And the area will be swept will be this much area that you can see. And in the second motion, let's say planet has moved from here to here in the next 1 month. The area swept will be the same. And the same thing can be shown also, it can be proved also mathematically, but that is not required, so we're not going into detail of that. You should know that this only, that the line joining will be sweeping equal area and equal interval of time. Let's go ahead after learning the second law. The third law is quite simple. And third law is based upon that planet is moving in an elliptical orbit. First of all, I was talking about this elliptical orbit. This is the first law. I told you that every planet is moving in an elliptical orbit. Now I have shown you two axes. In the last class I told you this is the minor axis, this is the major axis. Let me give you the length of this major axis as 2a, and let me give you the length of this minor axis as 2b. If E is the eccentricity of this elliptical orbit, what I'm going to mark here, let's say E is the eccentricity. If you are unaware about the term eccentricity, you will learn in the conic section chapter in maths. When you refer to conic section, when you study about ellipse, you'll understand about its eccentricity. Sun is lying at the one of the focus, its coordinate will be minus AE, 0. I can give you the coordinates, and that the same thing also we will study in conic section, minus AE, 0, and here the another focus will be AE, 0. This is where the focus will lie for an ellipse. Now let's refer to, I gave you all the names. Now see, this much length A, this is length A, this is length A. This is known as semi-major axis. This is length B, this is length B, this is known as semi-minor axis. Third law, the third law is law of periods, and again it's very simple. Third law of period, I'm writing here only. In this, we have, the law is very simple. We have the third law, the square of the time period of revolution around the sun is proportional to cube of the semi-major axis of the elliptical orbit. So third law says that square of time period I'm talking about the entire time taken to revolve all around the sun, square of time period of planet's revolution is directly proportional to square. I'm rubbing this part. This already I believe that you must have written down. E is the eccentricity of the ellipse is directly proportional to cube of semi-major axis. When I say semi-major axis, that means I'm referring to length A, semi-major axis. Hope that you are clear about the third law. It says the square of time period. Now see, square of time period is what? T square is proportional to semi-major axis, that it will be proportional to A cube. This is what as per the law states, that because semi-major axis here will be, we have taken total length of the axis as 2A, semi-major axis will be A, and this is semi-minor axis, that is B. So we are considering this as the term that I am referring here. T square is proportional to A cube. Now how to get it? We have derived all the equations treating the orbit as circular orbit, and we can idealize the situation. In case of circular orbit, what will be the case? The only change between a circle and an ellipse is this, that the radius of the circle will be equal to both the semi-major and semi-minor axis. That is, in this case, A will be equal to B, and that will be equal to radius of the circular orbit. The only difference between a circular orbit and an elliptical orbit. So if I try to prove it, we already know. We know for circular orbit, we have already derived this, we have already proved it. For circular orbit, T was given as, time period was 2 pi by under root gm and A to the power 3 by 2. This is what we have shown already, where A is the orbit of the circular path of the, actually the radius of the circle. The first question of the day, we have two spherical planets A and B have same mass but densities in the ratio 8:1. For these planets, the ratio of acceleration to gravity at the surface of A to its value at the surface of B is A 1:4, B 1:2, C 4:1, D 8:1. Let's check which of the option is given correct. I believe that you will be remembering what is the value of G. G is given as Gm by R square. So straight away we can write that Ga by Gb, that is action due to gravity at A to that of B, will be simply Rb by Ra whole square. So we need to find a relation between Rb and Ra. Given that both mass of A to mass of B is equal, mass of A is equal to mass of B, that's same. We know that mass is equal to density into volume. So we can write rho A into its volume 4 by 3 pi Ra whole cube is equal to rho B 4 by 3 pi Rb whole cube. This is what we can straightway show. This all terms will be cancelled out, we will be left with this one. We want Rb by Ra. Rb by Ra from here whole cube, Rb by Ra we do, we will be getting that as rho A by rho B. So Rb by Ra will be what? Quite obvious, Rb by Ra will be 8:1, and then you will be obtaining Rb by Ra is equal to rho A by rho B, and rho A by rho B is 8:1. So we need to do 8:1 par 1 by 3. This will be equal to 2. Now you see here Ga by Gb is Rb by Ra whole square. So Ga by Gb is equal to Rb by Ra whole square. So this comes out to be 4:1, because Rb by Ra is actually, that is equal to 2. So this will be 2 square is to 1. So hence this is 4:1. The right answer that is matching with the right option, that is 4:1. Let us check which of the option is correct. Option number C, that is 4:1. So you need to take 4:1 as your right answer. Stepwise proceed, you will get the right answer. Let's go ahead with the next question of the class. Before that, let me get the board ready for you all. So this is a way that you have to actually proceed with such questions. Let's go ahead with the next question of the day. 2. If G is the action due to gravity on the Earth's surface, just now we have did action due to gravity, the gain in potential energy of the body at a height equal to 2 times the radius r of the Earth will be. Understand the question. G is the action due to gravity at the Earth's surface. It's asking that on the Earth's surface, the gain in potential energy of the body at a height equal to 2 times the radius r of the Earth will be A mg2r, B mg3r, C 1 by 3 mgr, D 2 by 3 mgr. Let's see. First of all, we know that if this is Earth, if a body is placed here, let me show you. If a body is placed here, this is body A, this is Earth. Now you see here, we all know that the potential energy is given as minus G mm by r, where m is the mass of Earth, small m is the mass of this body. This is what we know, the potential energy of the body. When it is raised to a height twice the radius of r, height equal to 2 times the radius r, that means from center the height will be total 3r. So let me show you the final potential energy. That will be equal to minus Gmm divided by r plus 2r. This comes out to be minus Gmm by 3r. Do you have any idea which one is higher, which one is smaller? You see here in terms of magnitude, if we talk about the magnitude, since we have 3 here in the denominator, hence this will be smaller in magnitude. This will be smaller, and it is negative sign here, we have both negative sign. That means overall this will be higher. So the extra potential energy, the change in potential energy that you will be observing, that will be equal to potential energy final, the gain, so final potential energy minus initial potential energy. Let me say that this is initial potential energy when the body was at the surface of the Earth. Next thing, let us subtract it, minus Gmm by 3r minus, then this is minus Gmm by r. So minus Gmm by r. gm by r minus gm by 3r, you will be getting 2 by 3 gm by r. So let me show you here, this will be equal to 2 by 3 gmm by r. So as we proceeded, we got 2 by 3 gmm by r. So this is your right answer. So 2 by 3, and also it's given that mgr. Let us change the way the solution will look like. Gm by, what I will do, can we write this in this way? Gm by r square multiplied with r. We divided and multiplied with capital R. This term is g, it will turn out to be 2 by 3 mgr. So small m, small g, capital R. So the right answer that matches with the right option, that is D. So you need to mark option number D as the right answer. You will get full marks for this question. I believe that you have understood how to solve such kind of question. Next question of the day we have. Straight away let's proceed without taking more time. Next question of the class, third one. There are two bodies of masses 100,000 kg, that is equal to 1 lakh kg, 100,000 kg, and 1000 kg separated by distance of 1 meter. At what distance in meter from the smaller body the intensity of gravitational field will be 0? A 1 by 9, B 1 by 10, C 1 by 11, D 10 by 11. Now it's given that the masses are 1000 kg and 100,000 kg. And see, they may be having, it's not given that whether a point mass or not, we have to treat that these both are point masses, although they are of huge mass. M1, first mass 1000 kg. Then you have M2, the second mass, that is equal to 100,000 kg. Now it says that both are separated through a distance of 1 meter. This is the information that is provided. M1 1000, M2 100,000, and both are separated through 1 meter. At what distance in meter from the smaller body the intensity of gravitational field will be 0? From the smaller body, let's say at a distance of x, let's say this is point O, the gravitational field is 0. That means the effect of gravitational field due to both the bodies will be equal in magnitude but opposite in direction. So I am going to write G m1 by x square is equal to G m2 divided by 1 minus x whole square. This is what you need to do, because if this is x, this will be 1 minus x. That's quite obvious. Cancelled out, not a problem. M1 1000, M2 as 100,000. So you will be getting 1000 multiplied with 1 minus x whole square is equal to M2, that is 100,000 multiplied with x square. This is what you will be getting. From here you see here 30 will be cancelled out. You will be obtaining 1 minus x square is equal to x square. 1 minus x square is equal to 100x square. From here you try to observe, you will be getting an equation 1 minus x and its whole square. Just a minute, it's 1 minus x square is equal to 100x square. From here if you take square root, you will be getting 1 minus x is equal to 10x, 10x plus x 11x, 11x equal to 1, x equal to 1 by 11. So I am writing here x equal to 1 by 11 meter, that's the right answer. So the distance of x equal to 1 by 11 meter, the gravitational field will be 0. Option number C, that matches to the right response. This is how you have to proceed in the case of questions based upon gravitational field intensity. This is how you have to solve them. Straight away, let's switch to next question. Prior to that, just let me get the board ready for the next question. Next question of the class we have. Fourth one, if a body is released from a point at a height equal to n times the radius of the earth r, its velocity on reaching the surface of the earth is under root ngr by n plus 1, b under root 2 ngr upon n plus 1, c under root ngr upon 2n plus 1, d under root n plus 1 gr upon 2n. It's released from top. It says that n times the radius of earth. If released from a point at a height equals to n times the radius of earth, if I show you in the figure, how will it look like? This is the earth, This is the height from where it is released. This height is given as n times of radius of Earth, and here we have the radius of Earth as r. At both the points, the total energy will remain conserved. Potential energy here, potential energy and kinetic energy here will remain conserved. So, total mechanical energy at the initial position should be equal to total mechanical energy at the final position. This is what we can actually write. So, here at the topmost point you will be having potential energy only. Potential energy initial is equal to potential energy final plus kinetic energy final. I have not used kinetic energy for initial because the body will be at rest, it is released. Potential initial, that will be minus g mm divided by, you see here, minus g mm divided by its total height from the center of the Earth, that will be nr plus r, that will be equal to n plus 1 r is equal to potential energy final at this point minus g mm divided by r plus kinetic energy. Kinetic energy, that will be equal to half mv square, and that is what we need to evaluate. Its velocity on reaching the surface of the Earth is, we need to evaluate this. Let us write it as half mv square. We need to actually evaluate. From here you can easily cancel out this m terms, and if you write half v square, you will be obtaining half v square is equal to, take this term here, gm divided by capital R minus gm divided by n plus 1 capital R. So, gm by r 1 minus 1 upon n plus 1. I believe that this is what you will be getting. Easily you can solve it. You will be getting half v square is equal to gm by r square. Gm by r square is straightway, can you write that as we have done already, g into capital R, small g external to gravity into capital R, 1 minus n plus 1 minus 1 upon n plus 1, n plus 1 minus 1, you will get n divided by n plus 1. Next thing, half v square is equal to this, straightway v square is equal to 2rg n upon n plus 1. V square is equal to 2rg, you straightway see 2rg n upon n plus 1, n upon n plus 1, and straightway you can take its under root, you will be obtaining 2rg n upon n plus 1. You can proceed in this way, and let us check the required answer. You will be having, see here, it is given the 2nrg divided by n plus 1. 2nrg divided by n plus 1, this is what we are getting as the response. Option number B is the right answer. I believe that you have understood how to solve such kind of question. I want you all to see the solution once again. Check here the answer. Don't worry about, I have made here a bracket, it will be 2nrg divided by n plus 1. It's same thing. Don't worry about that. Next thing, before that, let me just clear the board. I believe that while practicing such question, it would be of great help to you all